Hello friends, welcome back to my channel. We are starting a new series of the basics of organic chemistry. So now we are going to see right from the beginning the origin of organic chemistry. So how has organic chemistry originated? Here in front of you, we are having the modern periodic table, and in this periodic table you can see almost all the elements, okay, and you just remove two elements from this. One is hydrogen and carbon. Just take these two elements apart, and when you take these two elements apart, you will realize that when you take hydrogen and carbon apart, okay, that is, they form something called as hydrocarbons. What do they form? Something called as hydrocarbons. Now these hydrocarbons were able to form so many compounds which the other 118 or 116 elements together could not form. Okay, so this is, you can call them as the two-man army. Okay, so these hydrocarbons are able to form infinite number of compounds which the remaining 116 elements also cannot together form. Okay, so that's how we come to the origin of organic chemistry. That's why it led to the formation of a new branch that is called as organic chemistry. So what are we going to do is we are going to see the basics of organic. So introduction to organic chemistry. Here, what does the word organic stand for? Organic stands for, it comes from the word organisms. That means it comes from life. So whatever is related to plants and animals will be coming under organic chemistry. So actually, whatever plastic also what you have today, the idea of plastic, that is, it is coming from alkenes, and that alkenes are found in plants. Okay, so although the plastics cannot degrade, they are of help. That is a debatable topic. Okay, they are of help or they are causing destruction of our nature. That is a debatable topic. But that origin has come from, the organic origin has come from, organic chemistry origin has come from the plants and animals. Whatever is found in plants and animals is organic. Like say for example, your hair, that's made up of keratin. That is again a protein that's coming under organic because it is having hydrocarbons. Then your clothes, they're made up of cotton. Cottons come under carbohydrates, and they are again coming under organic. Okay, then say for example, your wooden doors, your wooden tables, all these coming under organic. Paper comes under organic. Then your LPG gas, your fuels, okay, the fuel which you use for cooking, for traveling, all those come under organic. Petrol is nothing but octane. LPG gas is nothing but a mixture of propane and butane. Then candle wax is again a higher alkane which is containing more than 20 carbons. 20 carbon alkane is called as ecosane. Okay, so like that, this is originated to what? The hydrocarbons, and a separate branch of chemistry which is organic chemistry. So whatever is related to plants and animals will be coming under what? Organic chemistry. Then yeah, it is the study of compounds extracted from living organisms. So obviously organic compounds contain carbons. To be more specific, they contain hydrocarbons to complete the valency of carbon. So organic chemistry is also called as the carbon chemistry. Now why hydrocarbons together? Now we have now you check out this, all these are having carbons. Okay, all of these are having carbons. Are all of them organic? Do you call all of them organic? No, all of them are not organic. See, they are having carbons, but it is not following the properties of organic chemistry. Okay, so this is organic, this is inorganic, because just because they're containing carbons, that's not true. We'll shift a few compounds here, and then we'll see that only these are organic because they follow the properties of organic compounds, and these are all inorganic. Although they are containing carbon, they are inorganic because they follow the properties of inorganic compounds. So what led to the formation of so many compounds? How were hydrocarbons able to form so many compounds? So hydrocarbons were able to form so many compounds because of a unique property of carbon to form chains with itself, which is called as catenation. Right, so carbon was having the ability to form long chains with itself. So other elements are not able to show catenation. Yes, they are able to show. Like oxygen is able to show catenation only up to 3. Sulfur is able to show catenation only up to 8. It's called as the octaatomic sulfur. This is ozone. This is octaatomic sulfur, also known as crown sulfur, because it looks like the shape of a crown. This is crown sulfur. 1, 2, 3, 4, 5, 6, 7, 8. 8 sulfur atoms here. So it cannot catenate further than 8, beyond 8. So it is having a limit. But catenation in carbon does not seem to have a limit. It can go on catenating, and that's why so many number of compounds were being formed. Now, apart from catenation, another property of carbon which forms infinite compounds is isomerism. Right, another property is isomerism. Now what is isomerism? Isomerism, like, it's the, now here you are having like 1, 2, 3, 4, 5 carbons. These 5 carbons can rearrange themselves to form new compounds. Like with the same number of carbons I can form newer compounds. Like this is a new compound with the same 5 number of carbons, or I'm not completing the valency and writing hydrogen and everything. Okay, so here this is another compound with the same 5 number of carbons. So isomerism is what? Isomerism is two structures having the same molecular formula but different structural formula. Okay, the molecular formula is the same. With the same 5 carbons I was able to form different compounds, and with higher number of carbons the isomers also increased. So one thing was because of catenation, another thing because of isomerism, it led to an explosion of compounds, and that's why we had to form a separate branch called as organic chemistry. Now let us see what is isomerism in further detail. Yeah, let's talk about isomerism in further detail. So isomerism can be further classified as, okay, isomerism can be further classified as structural isomerism and stereo isomerism. Okay, structural and stereo isomerism. I'll just write that, structural and stereo isomerism. Okay, थोड़ा टेढ़ा हो गया, but you will understand, right? This is structural, and here we are going to have stereoisomerism. Okay, so in structural isomerism we are having 3 major groups, that is chain isomers, position isomers, chain, position, and functional isomers. Let us dive in deep into these 3 type of isomers. Okay, let's dive in deep into these 3 kind of isomers. So chain isomers are what? Chain isomers are compounds which are having the same molecular formula. I'll write down the hydrogens also this time. Okay, CH3, CH3, CH2, CH2. Okay, and this will be something like this: CH3, CH2, CH2 here, and one CH3 will place over here. Now can you tell me that is this chain isomerism? Okay, this is not called as chain isomerism. Okay, this is not an example of a chain isomerism. Why? Most of the children think that this is chain isomers. Like this is butane. Okay, longest chain, longest continuous chain, 1, 2, 3, 4, it's butane, and this is 1, 2, 3, or you start numbering from here and you call it as 1 methyl propane or 3 methyl propane, but it's not like that. This is a continuous chain. Okay, this is a continuous chain, it's the longest continuous chain. We did not have to jump anywhere. So this is also butane and this is also butane. You cannot call this as the longest continuous chain. Okay, then here we'll be having, like, if you put the branch on the second carbon, okay, so this is going to be the longest continuous chain, and on the second carbon we are having a branch, so this becomes 2 methyl propane. What does it become? It becomes 2 methyl propane. Now it is a different compound. Okay, 2 methyl propane, it's a different compound but with the same molecular formula as butane. So we will be having the similar, you can say, same molecular formula. Both of them will be having C4H10, but this is butane, this is 2 methyl propane. These two are different compounds, okay, but with the same molecular formula. So what you can say in definition of chain isomers: two structures having the same molecular formula but different branching or different chains of hydrocarbons. Hence they are called as what? Chain isomerism or chain isomers. Then okay, now, like, I was just wondering while teaching this that some of you don't know what is alkanes, alkynes. So I'll just tell you that in short and just quickly jump back to this. Okay, so this is like hydrocarbons. All of you know, like, hydrocarbons. We have just discussed that carbons and hydrogen together form hydrocarbons, and that's what led to the formation of organic chemistry. So these hydrocarbons have two kind of compounds, right? Which two kind of compounds? One is aliphatic, aliphatic meaning straight chain compounds, what we were seeing right now, and the other one is cyclic compounds. Okay, other one will be cyclic compounds. So aliphatic and cyclic. So what is aliphatic? Aliphatic mein kya aayega? Aliphatic mein we will be having alkanes, alkenes, and alkynes. We will be having what? Alkanes, alkenes, and alkynes. So what are this alkanes, alkenes, alkynes? Alkanes are the ones which are having single bonds. Alkenes are the ones which are having at least one double bond, and alkynes are the ones which are having at least one triple bond. These are the ones with the general formula, or the, you can say, yeah, general formula only, CnH2n plus 2, and this is having the general formula CnH2n, and this is having the general formula CnH2n minus 2. Let's see examples of alkanes, alkenes, and alkynes. So here we'll be having one carbon alkane, that is methane. Now you take the number of carbons is 1, so C1, 2 ones are 2 plus 2 is 4, so CH4, you get CH4 as the answer. So if you take this as 2, C2, then how many hydrogens are you going to have? 2 2s are 4, 4 plus 2 6, C2H6, right? So this is ethane, so this becomes the homologous series in alkanes: methane, ethane, propane, butane, pentane. We can go on like that, okay, with the number of carbons. Here in alkenes, the smallest alkene, we begin with 2 carbons, because we cannot have one carbon having a double bond with itself. That's not possible, okay? So that's the reason why we require minimum 2 carbons to form an alkene, and that is CH2 double bond CH2. This is an ethene molecule, okay? The molecular formula of this will be C2H4. Then we can have the next alkene member to be C3H6. Then we can have C4H8. This is like ethene, propene, butene, okay? Then for alkynes also we require a minimum of 2 carbons, okay? We require a minimum of 2 carbons. That is, this is ethyne. Ethyne is the smallest alkyne, also known as acetylene, common name. Ine is the suffix, here ene is the suffix, and here ane is the suffix. Ane, ene, and ine is the suffix. So the molecular formula for this is like C2H2. For propine, it is going to be C3, like CnH2, put it over here, 3, C3, 2 3s are 6, 6 minus 2, 4, C3H4. Okay, for butene, it will be like C4, put 4 over here, 4 2s are 8, 8 minus 2, 6, C4H6. So you can go on forming the successive homologous series. This is happening in aliphatic. Okay, in aliphatic, you can, these are all straight chain. You can also have straight, either you can have straight or branch chain. So you can have straight, okay, you can have straight or you can have branched chain, okay, straight or branched chain. Branched meaning you've just seen in the isomerism what is a branching, okay? So now apart from aliphatic, we have cyclic. Cyclic compounds are those in which the first and the last carbon are interconnected. Like say for example, we just saw butane over here, right? Butane was like 4 carbons together, that was butane. But in cyclic, butane will be like this. This is your butane, cyclobutane. Why cyclobutane? The first carbon and the last carbon are interconnected. Like what is a cycle? Come on, what is a cycle? You start pedaling, okay? So the point from where you start pedaling, you come back to the same point. When you come back to the same point, that is called as one cycle. Okay, so that's why cyclic structures are those that is we start with this carbon and we end on the same carbon. That means the first and the last carbon are interconnected. They are called as cyclic compounds. Then cyclic compounds can further be classified into, okay, cyclic compounds can further be classified into alicyclic and aromatic. I did not have placed there, that's why I'm writing over here, alicyclic and aromatic. So alicyclic compounds are those which do not follow the Huckel's rule. Okay, they do not follow the Huckel's rule, and aromatic compounds are those which follow the Huckel's rule. Now you must be wondering what is Huckel's rule. So Huckel's rule is simply, I mean, to explain in quick and short way, it is 4n plus 2 pi electrons. Okay, 4n plus 2 pi electrons. So like this double bond, every double bond is a pi bond and it is having pi electrons, and these pi electrons are highly unstable and they are forming an electron cloud. Okay, they are not unstable exactly, but they are moving all over the place and they are forming what? Electron clouds. So you can say that the benzene is having an electron cloud revolving around itself. Okay, so it's having an electron cloud which is moving. Okay, so that is the pi electron cloud. What it is? It's the pi electron cloud. So you've understood that every double bond is having 2 pi electrons. Now is this having a single double bond? No, it's not having a single double bond. Forget about having 4n plus 2 pi electrons, right? It is not having those many pi electrons, not having pi electrons at all. So it is what? Alicyclic. And this is what? Aromatic, because it is having 1 2 3 4 5 6. That means how to calculate this? N is the number of rings over here. How many number of rings are here? 4 ones are 4, plus 2, this is just to make you understand. So 4 ones are 4 plus 2 is 6, and 6 what, pi. Don't write pi over here as 3.14 or 22 by 7. You're not doing maths. Okay, this is pi meaning pi electrons. Pi electrons are the electrons which are present in the double bond. Okay, so this is having like 6 pi electrons. So 6 pi electrons, you count 1 2 3 4 5 6. Yes, it is having 6 pi electrons. If according to the Huckel rules, the number of electrons which Huckel rule is specifying, if that those many number of electrons are present in your ring, then your ring can be called as aromatic. One more condition of Huckel's rule is that your ring should be having bonds in conjugation. That means you cannot have a consecutive double bond like this. Double bond over here, double bond over here. That's not possible. That's not allowed in aromatic compounds. Okay, the double bonds should be in conjugation. That means they should be alternate, and they should have the specified number of pi electrons given by Huckel's rule. Then only it can be aromatic. Now there is more into it. Like this is all having carbons all over, right? So this is having carbons all over. It's called as homoaromatic. This is called as homoalicyclic. Now if you introduce heteroatom, generally heteroatoms are like Sun X. Okay, Sun X is the heteroatoms. So apart from hydrocarbons, if you are having like sulfur, oxygen, nitrogen or halogens, if introduced into our hydrocarbons, then they are called as heteroatoms or hetero elements. Okay, so like if you are having this kind of a structure, this is called as structure of pyridine. Okay, this is not benzene anymore. Earlier it was benzene, now it is pyridine. So it is heteroaromatic. It's aromatic, but it's having, instead of carbon, it's having a nitrogen over here. Okay, this is called as pyridine. Now most of the children get confused, like they call this as heteroaromatic. Now this is nitrobenzene. Nowhere is this heteroaromatic. This is very much homoaromatic. Why? Because inside the ring we are having carbons only. We have not replaced the carbons with nitrogen. In this case, we removed carbon from the ring and attached a nitrogen. We have inserted a nitrogen. Here nitrogen is just attached to the carbon, that to outside the ring. So the ring is homoaromatic, and here the ring is heteroaromatic. I hope you are getting the difference between the two. Same goes with alicyclic. Like alicyclic also can have a heteroatom. Na? Like see, you can have oxygen over here. Okay, that's a heteroatom there. So you can have hetero. This has become heteroalicyclic, and this will be homoalicyclic. So that's the difference between. I mean, that's a quick review of the hydrocarbons. That is aliphatic and cyclic. I've explained in detail about aliphatic and cyclic compounds. Now let's come back to our isomerism. We were doing structural isomerism. We just did chain isomerism. Two structures having the same molecular formula, but they are having different molecular formula. Okay, they're having different branches. Sorry, same molecular formula but different branches. This is a straight chain and this is a branch chain. You can't go, this is like straight, you can't go straight, and you cannot go like this, you cannot jump. So this is a branch. I have told you how to define a branch. So when there are branches or when there are different chains, they are called as what? Chain isomers. Now let's move on to position isomers quickly. Position isomers will be like the difference in the position of the functional group. So if like you are having the OH, that's the functional group here. If it is on the second carbon, then I'll call it as propan 1 all. Sorry, on the second carbon I'll call it as propan 2 all, and here I'm going to call it as, in the second case I'm going to call it as propan 1 all. So can you see the difference between the two, guys? Right, the difference between the two is like these two are having the same molecular formula. What is the molecular formula? Molecular formula is going to be C3H7OH. This is the molecular formula for both of them. So both of them are having the same molecular formula, but what's the difference? The difference is in the position of what? The functional group. Here the OH is on the second carbon, here the OH is on the first carbon. That is different. Position is different. Hence it is called as position isomers. I hope you're getting right. This is what position isomers. Then let's move on to functional isomers. Now what are functional isomers? Two structures which are having the same molecular formula. Of course, two structures having the same molecular formula but different functional groups. Have a look at this. CHO meaning aldehyde, right? So this is propanol, okay, having the molecular formula C3. Count no, C3, 3 carbons, hydrogens 2 plus 3 plus 2 5 plus 1 6. So C3H6O. This is the molecular formula, okay, and this is also having the same molecular formula. You can see that this is also having C3H6O. Both of them are having the same molecular formula, but what is different? The functional groups are totally different. This is an aldehyde and this is a ketone. Okay, so this is propanol and this is propanone, and hence this is called as what? Functional isomers. What are they? They are functional isomers of each other. Okay, they are functional isomers of each other. Two structures having the same molecular formula but different functional groups are called as functional isomers. So we have done the basics of isomerism just now. We have done the structural isomerism, chain, position, functional. We're going to move on to stereo isomerism. Okay, now what is stereo isomerism? In stereo we'll include, let me take it separately because we're falling short of place over there. So we'll take it separately. Stereo isomerism. So in stereo we will be having, stereo meaning 3D by the way. Okay, so we'll be having geometrical isomerism, and we are going to have optical isomerism. Geometrical and optical isomerism. Okay, so what is geometrical and optical isomerism? Geometrical meaning what? Two structures having the same molecular, I'm tired of saying this, two structures having the same molecular formula, but what? They're having different geometries. How are they having different geometries? Have a look. Okay, this is butene by the way. First carbon, second carbon, third carbon, fourth carbon. Correct? First 1, 2, 3, 4, and on the second carbon you are having a double bond. So this is butene, right? And if you draw an imaginary dotted line in between, an imaginary line here, and when you see that, okay, the groups on the above side are similar and groups at the bottom are also similar, so you call this as cis. What do you call it as? You call it as cis. So this is cis butene. Okay, and what will be trans? Like, oh, where did the line go? Okay, yeah. So cis butene, and then we'll be having trans butene. Like trans is what? Have a look over here. CH3C double bond CCH. No, CH3 will come down and CH will go up over here. So let me draw the dotted line in between over here also. So imaginary dotted line, and you can see that here we are having the CH3 groups. The similar groups are on the opposite side. If the similar groups are on the opposite side, still this is the same thing. 1, 2, 3, 4. So this is trans butene. This is also butene, but it is trans. Why? Because the similar groups are on the opposite sides. Similar groups are on the opposite sides. And here the similar groups are on the same side. Similar groups are on the same side. So when similar groups are on the same side, it is called as cis butene. And when similar groups are on the opposite side, it is called as trans butene. I hope you have got what is geometrical isomerism. Now, optical isomerism is something which I have explained in biomolecules part 1. Just I'll drop in the link in the description wherein you search for, you can just click on that link and you can see the entire optical isomerism. What is LIBO, dextro, what is chiral carbon, explained in super detail. Don't miss out on that. To understand optical isomerism, I've explained that in biomolecules part 1 of my video. I'll be dropping that link of that video in the description. Thank you.